Have you ever wished that a simple puddle of fluid could instantly turn into a solid wall of resistance, and then right back into a free-flowing liquid totally on command? Well, welcome to this explainer where we're going to demystify exactly how smart materials can pull off this magic trick in the blink of an eye. Today, we're diving straight into the fascinating science behind electrorheological and magnetorheological fluids, or, ER and MR fluids for short. These are some seriously incredible smart materials that are quietly revolutionizing everything from the car you drive right down to the massive skyscrapers you might work in.
Real quick, here's our roadmap for today. First, liquid to solid instantly. Second, we'll look at the secret microscopic mechanism. Third, the physics of flow. Fourth, ER versus MR fluids. And finally, number 5, real-world engineering applications. Let's get right into it.
Starting off with Section 1, liquid to solid instantly.
Now, what is truly mind-blowing here is that this field-controllable change, which scientists call the rheological effect, requires absolutely zero moving parts to work. Under normal everyday conditions, these materials behave just like an ordinary liquid, maybe a thick paste. But the absolute second an electric or magnetic field is applied, boom, the fluid stiffens up dramatically. We are talking about it turning almost completely solid in literally just a few milliseconds. And the best part of all this is that the moment you remove that field, the fluid instantly snaps right back to its original liquid state. This means wherever a mechanical system needs variable damping or resistance, we can tune it electronically, instantly, without relying on any of those clunky traditional pistons or linkages.
Okay, moving to Section 2, the secret microscopic mechanism.
So to actually understand this magic, we have to zoom way in and look at the fluid's composition. Both ER and MR fluids are, at their core, just suspensions. They're made up of a massive number of micron-sized particles floating around in an inert carrier fluid, like silicone or mineral oil. In their resting, off state, these particles are just scattered randomly all throughout the liquid. In fact, the source material describes it perfectly. It's exactly like sand suspended in water. The carrier fluid's only job is just to keep those particles suspended. It doesn't react to the field at all. And because there's nothing holding the particles together in this resting state, the mixture just flows freely with a super low viscosity. But when you flip that external field switch on, everything changes in milliseconds. It's this brilliant self-assembly process. The individual particles suddenly become induced dipoles. Basically, they develop a positive and negative charge, or a north and south pole. Once they're polarized or magnetized, all these neighboring particles naturally attract each other tip to tail. They rapidly snap together into fibrous chains that stretch entirely across the fluid gap, completely parallel to the field. And if you up the particle concentration or turn up the field strength, these chains actually thicken into really sturdy microscopic columns. Let's look at how that actually behaves in Section 3, the physics of flow. So, the absolutely crucial point here is that those particle chains we just talked about, they resist breaking, which acts as a literal physical barrier to flow. The standard way engineers describe this activated state is the Bingham plastic model. Actually, just think about squeezing a tube of toothpaste. It won't flow out until you apply enough physical pressure to overcome its yield stress. Now imagine trying to push a layer of this smart fluid. Because those tiny microscopic columns are actively bridging the gap, the material outright refuses to flow until your pushing force, your shear stress, exceeds that yield stress. And here is the real kicker. You get to tune that yield stress entirely with electricity. Just by dialing up the voltage or current, you directly control the exact physical force required to make that fluid move. And this mathematical translation right here tells us exactly why the fluid's stiffness spikes so steeply when you turn up the voltage or magnetic current. The governing equations show us that the attractive force between two adjacent aligned dipoles doesn't just grow linearly step by step, it actually grows with the square of the applied field strength. That is an incredibly powerful relationship. It completely explains why a relatively small dial-up in the electric or magnetic field results in this intense, steep spike in the fluid's yield stress, right up until those particles hit their maximum physical polarization.
Which brings us to Section 4, ER versus MR fluids.
While the general recipe is pretty much identical, particles suspended in an inert oil, the big difference comes down to whether we are polarizing the particles with high voltage or magnetizing them with a magnetic field. ER, or electrorheological fluids, use polarizable dielectric particles, like silica or certain polymers, and they're activated by an electric field, which is usually generated by high-voltage electrode plates. On the flip side, MR, or magnetorheological fluids, use micron-sized ferromagnetic particles, typically carbonyl iron, and these are activated by a magnetic field, usually created by an electromagnetic coil.
Now, if you take a look at how their properties stack up, you'll see MR fluids offer some massive performance advantages, especially when it comes to durability and shear holding force.
See, while ER fluids require super high voltage and happen to be highly sensitive to temperature drops and fluid contamination, MR fluids operate on low voltage and a higher current. But even more importantly, MR fluids are remarkably stable over a really wide temperature range, and they are way less sensitive to impurities or moisture. So if you're taking these out of a pristine laboratory and putting them into real, messy, heavy-duty engineering environments, MR fluids are significantly more robust.
And reaching an upper limit of around 100 kilopascals is exactly why MR fluids have become the absolute go-to for that heavy-duty engineering. To put that in perspective, ER fluids typically only reach a yield stress of about 2 to 5 kilopascals at practical field strengths. But MR fluids, they can reach a massive 100 kilopascals at fields around 1 Tesla. That is a vastly stronger structural hold, which allows MR fluids to physically resist immense mechanical forces without giving way.
So, let's see this in action in Section 5, Real-World Engineering Applications.
Because the response time here is just far, far faster than a conventional mechanical valve or a servo-controlled hydraulic system, these fluids are unlocking adaptive, real-time control right across massive industries. Remember, we are talking about microscopic chain formation and collapse happening on the order of a few milliseconds. That literally means the dampening force of a giant machine can be adjusted hundreds of times per second, dynamically reacting to its environment exactly as it changes.
I mean, just look at this list, from softening the brutal bumps on your daily commute, to actively earthquake-proofing a massive skyscraper, to giving a prosthetic leg a perfectly natural gait. The real-world scale of this is mind-blowing. In heavy trucks and even production cars, MR fluid dampers are continuously adjusting ride stiffness in real time based on the road conditions. In infrastructure, you have massive MR dampers actively counteracting wind and earthquake vibrations in buildings and bridges. They're replacing old mechanical linkages in fast-responding clutches and brakes. In high-tech manufacturing, MR fluid loaded with abrasives is even used for nanometer-scale optical polishing. They can literally tune the stiffness of the polishing tool perfectly to the lens. In healthcare, these fluids allow prosthetic knee joints to adapt instantly to a wearer's walking speed. And over in the tech sector, both ER and MR fluids are generating programmable resistance for haptic feedback joysticks. It's truly everywhere.
So I want to leave you with this thought. If a simple liquid can be electronically tuned to instantly absorb the shock of an earthquake, what other rigid structures in our world are just waiting to become smart and adaptable? Thank you so much for joining me on this explainer. We've seen how just suspending tiny particles in oil and applying a simple field can create these instant structural columns that are revolutionizing everything from optics to architecture. I hope this leaves you questioning just how dynamic the seemingly solid objects around us could really be, and what the future of engineering looks like when our materials can think and react just as fast as we do. Keep exploring, and I'll catch you in the next one.